Okay, let's continue this lecture with the microstrip antenna, and in particular, I want to identify E-plane and H-plane of microstrip antenna. So remember that this was our microstrip antenna that we studied in the previous two lectures. So this is essentially the metallic ground plane. This is our substrate, and then this is essentially our three-dimensional structure. Now we're gonna get to microstrip antenna. For example, this is an inset fed. So, and if you remember, this was the length, which was close to half a wavelength. This was the width, and the dimension that we considered previously was this one was X, this one was Y, and this one was Z. So if I go by this dimension, and if I look at from the top from the antenna, then I see a structure like this. Forget about this inset. I mean, this is important, but for the E-plane and H-plane discussion, we just ignore it for now. And then we had fringing effects like this. So that was our fringing effects. So you see, you have two sets of electric fields at these two edges that they essentially create radiation for you based on this based on the way that we identify this is Y, this is Z, and X would be outside from the surface. Now, so this is Rx. Now, if you look at the way that they radiate, first of all, you notice that these are in phase. So if I'm on the x-axis right here, the distance from the observation point on the x-axis to this radiating slot or this radiating slot are the same, and also they have the same phase. So essentially, they add constructively over the x-axis. So everything would be in phase on the x-axis. So x-axis is going to be the direction of the maximum radiation. So this is the x-axis. So I already know that's the x-axis. Now, to identify E-plane, I'm going to ask myself, what is the direction of the electric field? This is obvious from here. These are electric field in this direction, so is in the Z direction, or minus Z in this particular plotting. Doesn't matter, it's along Z. So electric field is along Z, and I have my X. So therefore, E-plane would be combination of the direction of electric field and the direction of maximum radiation. So I'm going to get XZ for my E-plane. So this cot here, so this cot, which consists of X and Z, so this cot here, that would be my E-plane. So if I want to measure the radiation pattern of this antenna, the E-plane, essentially I'm measuring over this plane right here. And remember, if the ground plane is infinite in size, then there is no back radiation, but that's not the case. So it has a finite side, and therefore you get some back radiation. And perhaps because of the effect of finite side, you might get some rippling effects also in the radiation pattern. So that's my E-plane. And similarly, therefore, H-plane, so considering that H is perpendicular to X, so if this is my E like that, so therefore that would be my H, which is in the Y direction. So H plane would be XZ based on this coordinate that I have. So XY, sorry. H plane would be XY. So on the x-axis, I have the maximum radiation, and on this, the electric field would be this, corresponding to this, and H would do that. So you're going to have your plane wave going in this direction. So EH and direction of maximum radiation. So this is the E plane and H plane. In the textbook, the way that is defined in the textbook is a little bit different. I think this is the coordinate, in the textbook. So this is X, this is Y. So if that's X, that's Y, then that would be Z. So this is gonna be Z in this way. So it depends how you define it, but the way that has been defined in the textbook is this way. So you might get different things in the in the textbook. And also we do measurements for patch antenna in one of the labs. I don't exactly remember what was the coordinate, but you get the concept that this is your E plane and H plane dependent on the way that you define your coordinates. So the other thing that you're gonna look at the radiation pattern in a few minutes when I show it on the computer is comparing E plane and H plane cut. So something that you could immediately see here is that if you look at this radiating slot here that you have is in this shape almost. So this antenna, let me talk about this antenna within this framework. So you essentially have two radiating slots separated by about half a wavelength. And on these radiating slots, you have like an electric field, which in the way that I'm plotting is a uniform electric field. So you have that essentially. And if you look at this, this is your delta L, which is very tiny. We calculated that. So remember, you had this L. This was due to fringing effect. This was due to fringing effect. So this is extremely tiny. And this is that you have is of course is not tiny. That's in this case your W. So it's comparable to wavelengths. So now if you look at your E plane, and if you, this was my E plane, so if you make a cut in the E plane, you see that the size of the antenna, at least one of the radiating slot in the E plane, is this much. This is the size of one radiating slot in the E plane cut. But if you consider H plane, which was this plane here, so this was your E plane, this is your H plane. If you consider H plane, the size of one radiating slot in the H plane is essentially this much. So this is the size in the H plane. This is the size of the antenna in the E plane. So if you look at, you see that the size of the antenna in H plane is bigger than E plane. So when you look at the radiation pattern in E plane and H plane cut, keep this in mind that if you see a more focused beam in the H plane, you could attribute it to the fact that the size of the antenna in H plane is bigger than E plane, at least for one radiating slot that we studied here. So the larger the antenna has the potential to be more directive, to be more focused. So that's why in H plane you see a more focused beam. And you could also connect it to the dipole antenna simply. If this is my dipole antenna, H plane is perpendicular to the dipole. So if you consider your H plane, this is your H plane. So if you make a cut of the dipole in the H plane, what you get is just a point. What you get is just a point, and a point radiates uniformly everywhere. So you get omnidirectional pattern in the H plane. But E plane is, for example, this is your E plane for the dipole. You actually see the whole length of the dipole, and therefore you get, for example, a pattern like this. So in the H plane, the size of dipole is so tiny, it's just a point. Therefore, it becomes omnidirectional in this cut. So this is the discussion on the size of the antenna that you can consider. The other thing that you can immediately see from the discussion of microstrip antenna here is that, first of all, this is like an aperture antenna. So this is like an aperture antenna with two apertures of electric field. So aperture antenna, you have an aperture, and on this aperture you have an electric field distribution, and that's going to radiate for you depending on the way that you design this electric field. For example, you design this electric field to be in phase, so they have certain characteristic. For example, the main beam is essentially perpendicular to the patch, but you could also have electric field with some other distribution, and then you can change the way that it radiates for you. We're going to talk a little bit about that. But my point here is that this, you can think of this as an aperture. You can think of this an aperture, and then you can think of their collection as a two-element antenna array. And each element of the antenna is essentially one radiating a slot of the microstrip antenna. So you have a two-element antenna array. Each of them are like that. And also, it's backed by a ground plane. So the same way that monopole antenna was backed by a metal, now you have an aperture that's backed by a metallic ground plane. So, and if you remember, in monopole antenna, because we had a ground plane here, we got higher directivity compared to its corresponding dipole antenna. And this ground plane plays a similar role for us. It increases the achievable directivity for us. So that's one way that you can actually estimate the directivity associated with your structure, that you have two-element antenna array. So you could potentially get a factor of 2 because of that. And you remember the directivity when it comes to arrays are not that easy. You need to calculate, but at least we know that roughly speaking, you can get twice directivity because you have two elements. So if you know the directivity of this element, you know you have a ground plane that enhances the directivity. For example, in the case of monopole and dipole, it increases by 3 dB, and then you potentially can double the directivity or adding 3 dB because you have two elements here. So before we look at the radiation pattern of E-plane and H-plane, let me mention something else, and I'll come back to this at a different time. The one thing I wanted to mention is that I'm going to go by the coordinate of the textbook because I want to refer to the textbook for this. So if I go by the coordinate of the textbook, essentially here I'm going to have Z and then I'm going to have Y here. So if this is the coordinate of this system, I'm going to have Y here because this is along Y. Remember, these are my fringing effect. So these are my Y and this is my Z. So this is my Z and X is still like that. So this is the coordinate in the textbook. So if I consider that, now textbook has given you the total electric field of this structure. It's a long calculation. Hopefully I'll get to that after I'm covering another type of the antenna. You see the reason, but imagine you want to look at the electric field of this antenna system. Then perhaps you could identify one component in this electric field. Remember, I said you can think of that as a two-element antenna array. So if you have two-element antenna array, you can say that perhaps you can say the electric field is E of single element multiplied by the array factor. An array factor is a two-element, number 1 and number 2. So you have a system like that. So this is your single element times array factor. Now, what would be array factor? Let's talk our array factor. Array factor based on array discussion, we remember that this is our array factor. Now, if n is 2, therefore I can simplify that to 2 sine psi 2 cos psi 2 divided by sine psi 2, and therefore I'm going to get 2 cos psi divided by 2. And this 2 is an indication that with array factor you can double the total electric field. And your psi is kd cos theta plus beta. Now, I want to explain what is our array factor in this particular case that we have. So what was the assumption when we derived this in the array part of the course? The assumption that we had was that the array elements are on the z-axis. So this was the array element along the z-axis. So if this is my assumption, that's actually the reason I get cos theta, because if you go through the formulation, you see that this cos theta appears for the fact that if your observation point is here, this is along r hat, and then the array element are along z, so you have a z hat here, so and then this angle is theta, so r hat dotted with z hat, you get your cos theta here. So now, but in this situation, based on the coordinate of the textbook, the elements of the array are not along z, they're in fact along y. Look at this y, you have one here, you have one here. So if I plot that, and you remember perhaps that array factor has nothing to do with the type of the element, so I can just put a point here. So this is my array structure right now. So it's not going to be along z, it's in fact along y. And that's why you need to change this cos theta. So when it was along z, we had r hat dotted with z hat, but now that is along y, naturally you're going to have r hat dotted with y hat. And if you do this, you get sine theta sine phi. That's going to be r hat dotted with phi hat. So in this expression, you're going to change cos theta to sine theta sine phi. And that's your sine theta sine phi. And what is beta? Beta is the phase difference between these two. But we mentioned in the previous lecture that these are in fact in phase. So the phase difference is 0. So you get actually kd sine theta sine phi. So then the question is, what is d? In the textbook, d is substituted by le. So, and then if you go a few pages back in the textbook, you see that this LE is L plus 2 delta L. So that's the effective length, which is this one is your L. And then for fringing effect, you have some extension of length, which is delta L here, delta L here. It's going to make it L plus 2 delta L. So if you look at the expression of electric field, you're going to see this factor, which is 2 cos K is 2 pi lambda, D is LE, and then you get sine theta sine phi. So sine theta sine phi, and that's going to be the array factor. So you can easily identify the presence of the array factor. And as I mentioned, if you want to see what's the effect of two elements in the directivity, you essentially need to go through calculation. But roughly speaking, we might say that because it's array, because it's a two-element array, it has the potential of increasing directivity by about a factor of 2, which is 3 dB. So that was my previous discussion. So I wanted you to see this. And let me also mention something else. If I change the coordinate such that now this y becomes x, now my element is along x-axis, therefore this needs to be changed to r hat dotted with x hat, which is sine theta cos phi. This is one more thing. Now to wrap up my discussion, let me also remind you that epsilon r is very important, because wavelengths, when you calculate wavelengths, you're going to rely on epsilon r effective, and epsilon r effective is affected by epsilon r. So if you increase epsilon r, then wavelengths drops. And because everything is with respect to wavelengths, then size of the patch and everything drops. So you can get some, the size gets smaller if you use, for example, a substrate of 10 epsilon 10 versus epsilon 2. The size drops, but this has some also negative effect. For example, the bandwidth gets worse when you increase the dielectric substrate. So now let's go and look at the radiation pattern that I promised. I'm going to show it to you from our textbook by Professor Balanis and Wiley as the publisher. So let's look at that, and then we're going to continue our discussion.
Okay, let us now check the radiation pattern of microstrip antenna using a figure which is in our textbook by Professor Balanis and Wiley as the publisher.
Okay, now that we talked about this radiation patterns and so on, let's look at one specific form of microstrip antenna, which is known as PIFA, planar inverted F antenna. So to explain PIFA, let's consider a few things first, and then we're gonna go to PIFA. Okay, so you see, sometimes you perform some variation on some types of antennas, and then you can connect, you can essentially make connections with other forms of antenna, and that's what I'm trying to mention here. So imagine you have a quarter wavelength monopole antenna. So this is essentially, assume that this is your quarter wavelength monopole antenna here. So this is my PEC ground plane, and this is my quarter wavelength monopole antenna. Sometimes in some applications, an alternative form of that is to have to bend it like this. So I mean, so this is called inverted L antenna. So inverted L antenna. And so they get this quarter wavelength dipole antenna, and you bend it and you end up with inverted L antenna. Another variation of this is to do the same thing, but this time you're gonna have a shorting pin as well. So like that. So this is essentially the shorting pin that you add. So you see this is like a very tiny transmission line, short circuited. So this is inverted F antenna. So you see the letter F, but inverted. So this is letter F. You see a very similar structure to that, but that's inverted. If you want to understand this stuff, you can perhaps use transmission line theory to understand it. And for example, this part of this, you can think of it as a transmission line short-circuited, and this part is very tiny. So this is a tiny length. So if you look at here, Z in is going to be Z naught plus J ZL tangent beta L, ZL plus J Z naught tangent beta L. We know that ZL goes to 0, so we can ignore ZL because that's short circuit. Z naught and Z naught cancel, and you get JZ naught tangent beta L. Because this is tiny, then this becomes essentially positive. So your Z in becomes a positive J, which is similar to an inductor. So this part you may think of it as an inductor. So, and then this part you may think of it as an open circuit, for example, a transmission line open circuited, and the length of this transmission line is going to be less than lambda divided by 4 because we started with lambda divided by 4. So this part is going to be less than lambda divided by 4. And so I'm going to have a similar situation, but this time ZL, which is this load here, is open circuit, so it's very big. So this is going to be dominant, this is going to be dominant, and you're going to get Z naught divided by J tangent beta L. So you're going to have this, you're going to have this, and you're going to have this because your ZL is huge. Now, based on this, you're going to get minus j z naught tangent beta L. And this beta L is going to be 2 pi lambda, and L is going to be less than lambda by 4. Therefore, this tangent would be tangent of 90 degrees. This is 90 degree minus something, and therefore tangent is going to be positive. Because tangent is positive, you have a minus j here, so this is going to be like a capacitor for you. So, and then if this structure radiates, you essentially have a resistor, radiation resistance, and you get your RLC demonstrating this structure. But anyways, sometimes you have an antenna and you go to different evolution of that to get the things that you want for it. So, and then you always pay a price for something, and that's one type of evolution. Now, let's consider the same concept for microstrip antenna. So in microstrip antenna, I had this metallic ground plane. I had this substrate, and this was my patch. And we said that this patch was about half a wavelength. And based on this half a wavelength assumption, we use transmission line model to say that voltage distribution here is equivalent to something like that, because this is almost half a wavelength. So you get half of sine, and here is open circuit. You assume voltage is maximum, then the same thing here. You also assume voltage is maximum, and therefore you can assume that voltage at the center crosses zero. So that's what we have. So then the idea is that because it crosses zero, you can essentially connect this using a shorting pin to the metallic ground plane. And if you do that, and then remove this part of the substrate, nothing will change on this side. So this side remains the same because you apply the necessary boundary condition. So remember, without this shorting pin, it was automatically zero because you had half a lambda voltage. So this was a half a lambda voltage going from Vmax to minus Vmax. Now, if you, of course, remove it, and you want to keep the same structure for the half, you need to apply the correct boundary condition here, which is voltage zero. So you connect these together, and then you just keep this part. So that's essentially what's happening with this. So that's give you the same voltage. Now, this is, of course, without feeding a structure of the antenna. But now let's consider the feeding of that, and that makes my point more clear. So let's consider a probe fed. So we said if you want to feed this antenna, this is the center of the antenna. So we're not going to feed it at the center. We're just going to be a little bit off center. For example, if you could be here, feed at this point, or you could feed, for example, at this point. So depending on which part of the patch you want to keep after turning into PIFA. But if I'm not mistaken, let me go by the style that I did for the teaching of the feeding of the patch antenna. So I think back then I had my probe here. So I said this is a probe fed. You bring a coaxial cable from the back. The inner conductor touches somewhere here. So if you feed from here, then you're gonna have a large input impedance. It's difficult to match, so you do a little bit of offset. If I'm not mistaken, we called it Z0. So now, based on this excitation, now I have my electric field distribution. And again, if I consider my transmission line model, this is the voltage that I'm going to get along the patch. So now, if I want to get rid of half of the patch, I can get rid of half of the patch, but voltage here goes to 0. So if I get rid of half of the patch and I want to keep everything the same from this viewpoint this time, I need to apply my shorting pin here to create voltage 0 here. So that's then half of the patch is already gone now. So now you see I applied boundary condition here so that I don't need the rest of the patch. And now if you look at that, you see an F here, which is essentially the same concept as inverted F antenna. But this antenna in this case, I mean, this is just a cross-section view. This is a plane. So this is essentially continuing like that. So I wanted to just, I wanted for you to see the connection to this inverted F antenna. But anyways, the idea here is that you can remove half of the patch. So you can cut the size of the antenna by half. Of course, if you do that, then you're not going to have two sets of radiating slots as you had before because you've already cut half of it. So this is now gone and you have one radiating slot and this is now connected to the ground. So I mean, I'm going to put this here to say that this is essentially shorted to the ground because we wanted to make sure that still we have a zero voltage at this point. So now we have only one radiating slot, and of course, the other antenna is more is better in terms of directivity and things like that. But this might be better in other aspects. For example, for wireless communication, you need to satisfy a safety criteria named a specific absorption rate, or SAR. So now, I mean, these two antennas would be different in terms of a specific absorption rate when they're radiating into the body. So that's our planar inverted F antenna, or PIFA. So this was inverted F antenna, and this is the planar version of that. So that's something that you can consider. Similar to this style that we consider a circuit model, you could also discuss circuit model here by saying that, for example, in a patch, you can consider this as one length of transmission line. You can, if this was a full patch, you can consider that as a different size of transmission line, and so on, and understand it from circuit viewpoint. This simplification could help you understand the system better. And finally, remember that in circuit courses, we talk so much about RLC. And now this is nice because we can understand that complicated structure like patch antenna can be modeled by an RLC circuit, because essentially we can think of it from transmission line point of view, and from one side they might be an inductor, from another side they can be capacitor. Resistance could be your radiation resistance, or your losses within the antenna. So this RLC that we had in circuit courses is also applicable to more complicated structures such as antennas. So this is my discussion regarding inverted F antenna and planar inverted F antenna. Thank you.
Okay, so we talked about PIFA in the class. I just want to make a point regarding the design equation for PIFA. So I'm just going to rely on the PowerPoints of our textbook. So let's check a couple of PowerPoint slides from our textbook.